Hello, everyone. I'm Lapo Frati, and I'm happy to present this work from Cengiz Petak and Nick Cini, which some would say puts a new spin on an old idea. I'm sure all of you are familiar with elementary cellular automata. If anyone is not, it's a simple yet interesting model, one-dimensional, which is great. Leaves another dimension on the page so that you can see time evolving. Binary states, so looks great, black and white. And the neighborhood is really small, so it's easy to compute, and some people used to do it by hand. You can see a little GIF showing how it works here on the right. And because the neighborhood is only 3 states, there is like 2 to the 3, 8 possible states, so 8 bits are enough to specify one of these rules, and there are a whopping 256 possible rules in these little icons. You can see again, as I mentioned, time going down, and each row is one state. However, when you implement this and run them, you have to make some decisions what to do mostly when you get to the edges. You have 2 main options there. You can pad with a fixed value, or you can apply some periodic boundary conditions, so looking over all the way to the other end. One of those options is clearly superior. The looping boundary conditions, for example, avoids some artifacts. In the case of this specific rule, you can see that if you have a constant padding, you would introduce some artifacts. But most importantly and relevantly to this talk is that you turn the sequences into necklaces. Necklaces, if everyone has ever heard the term, means an equivalency class of the binary strings taking all rotations as equivalent, which means that the sequences which have a different beginning and end now instead have no beginning or end, and they're just forever spinning. The work started from a very simple problem. We wanted to sample some initial states for these elementary cellular automata. And how do you do it? There's an obvious solution, which would be to just sample a random from the set of black and white states, which gives you all these nice initial conditions and let you run your ECA rules on them. However, if you sample a few of these, you might notice that some of these patterns look quite similar. For example, I'm sure everyone can spot the difference between these 2 ones. And of course, they're similar because, as I mentioned, one is just a rotated version of the other, which a bit more formally is just to mean the rotation, shift, and application of the rule commute. If you shift and do the rule, or if you do the rule and then shift, is the same thing, which means that these loops are just the same. So this begs the question, I wonder which of these sequences are actually the same under rotation. And let's see what mathematicians have to say on the topic. If you do a quick search on the online encyclopedia of integer sequences, you can find the entry number 31 is the number of n-bits necklaces with 2 colors when turning over is not allowed. So our setting, and they provide like a nice formula. But this formula maybe is not so nice because it has the Euler-Tothian function in there that counts numbers that are prime to that number, which to me is not the super intuitive kind of function. So maybe we can have an easier understanding of what these things look like and how many of them there are. Here on the right, you can see the necklaces and the corresponding sequences. So the one on the left is the equivalence class. The options are just to have 1 element per necklace, like in this case where everything is white, exactly n elements. In this case, n is 4. And you can have some intermediate states when you have some periodicity. If you check how many of each one of these cases you have, you notice that as the n grows, almost all equivalence classes have n elements. So because there are 2 to the n possible sequences when the value of n grows, you have 2 to the n over n necklaces, which has pros and cons. Pro is that the reduction could be to 20 or 30 times. The con is that they still grow exponentially. How are these necklaces distributed? In order to get a feeling for what they look like on the number line, we need to like assign 1 unique number to each one of those. We have used as the representative for each necklace, the sequence that has the smallest decimal representation. So basically what you're doing is that you're trying to put as many white cells on the left so that like the number that it represents is as small as possible. And here you can see on the left, there is the decimal representation, the binary, the corresponding necklace, and then back to the decimal representation of that, which allows us to plot the necklaces on the number line. So X here is on the X-axis and On the Y, you have the representative of the necklace, and you can see how it has a very satisfying self-similar structure, especially if you zoom in, you can see a lot of interesting patterns, which is why some of the algorithms developed for computing these structures are recursive in nature. I talked about necklaces, but the title of the paper was also mentioning networks. How do we go from one to the other? As I mentioned, the equivalence class of the application of a rule to a state is the same as the application to the rule to the equivalence class of the state. As I was mentioning before, these two commute, which means that if you take your states and you group them in necklaces and you draw in red the transitions from one state to the other, all the arrows that start from one group end in the same group, not in the same one, but the fact that they all end in the same one allows you to represent them as sort of coarse-grained version that you can see in the thumbnail up in a smaller in the corner. And if you consider this coarse-grained version, you can see that the reduction of nodes is pretty significant. As you can see here, there's a comparison between all the nodes and the necklaces only, and it allows you to see more clearly what is the structure underlying these rules without all the noise of additional redundancy. So we also try to take a closer look. There's so many things we could investigate, but we have decided to focus on a couple of ones. For example, what kind of structure do these networks have? Are all the nodes part of a single weakly connected component? If not, what do these components look like? In this case, we use weakly connected because these are directed networks. So we use this more relaxed version of connected component where it's okay to just have a path between any two nodes. Doesn't have to be both ways, and it's going to be apparent why it matters in a second. Let's say you want to assemble your own little cellular automata, and you're given the rules, which since they're deterministic, they cause each node has a single successor. So you have this lollipop structure, and you want to make a long sequence without any loops in it. So you start trying to assemble your long little chain, but at the end, what do you do with the last one? You have to connect it somewhere. If you connect it on itself, you create a loop. If you go backward, you still create a loop. So you have to have at least one loop in each one of these components. Can you have more than one loop? Actually, no, because the fact that you have a single successor makes it so that if you are on a loop, you have one edge that needs to keep you in that loop. And by definition, you're not going to have anything allowed to exit, which means that each one of these components is always going to have some core loop inside. And there are going to be many possible ways in which you can get to that core loop, which could be a self loop or a longer sequence. The representation with the networks of necklaces here is shown on the right of each one of these two slides. And on the other side, you can see the sort of sequence representation. I have highlighted in red the states where a loop begins and ends. And I can not really tell, looking at the sequence, that I actually went back to the same thing, just rotated on the x-axis. But if I look at the sequence in the network space, I would say it's pretty obvious that you went through an entire loop. The one on the right is an example of a sequence that comes from, of a network that comes from a different rule. In this case, we didn't complete an entire loop, but you can still see in red the nodes that we went through. You can ask yourself, okay, can all these nodes all converge in the same component or be part of the same large component? It's unlikely, but there are some rules for which this happens sometimes. In particular, I don't know if any of you has ever noticed, but if you pick rule 90 for sequence length that are powers of 2, then you have this beautiful tree structure where you can see the little loop right at the heart of it, and everything else sort of converges into it, which is a bit of a pain to plot because there's a lot of nodes in there. If anyone tries to open the PDF, there's going to be a beautiful animation of all them appearing one at a time, but it's kind of satisfying. Other possible structures, here I'm showing a couple of examples of some rules. For example, rule 110, very popular. Many people love to investigate. It's computational capability. On the left, we can see it's an example of starting from a random state of its evolution. And on the right, we can see how the largest weakly connected component changes as we increase the length of the sequence. So n goes from 8 to 16. Other rules have different behaviors. That one was very, very branchy, very tree-like. These other ones instead like to generate less interesting maybe in this representation, but still quite cool, like little loops. This is rule 45 that we are seeing like all the weakly connected components, not only like the largest one. And you can see that creates like a lot of like tight little loops. They look smooth, but just because there's a lot of like nodes in them. Since we have been talking about loops, we can ask ourselves who are the most uniquely loopy rules, because having a lot of loops per se is not necessarily a good thing, because the rule that does nothing, it's just a collection of self loops, then it's not particularly interesting. It would have a lot of loops, but very boring ones. So we wondered which one have the largest number of unique loop lengths. And we noticed that there are certain rules that have a clear head advantage over the others. Here you can see their average ranking by number of unique loops over several orders of magnitude, because of course, as you change the length of n, some behaviors can change. And some of these rules, unsurprisingly, have a very chaotic behavior, which allows them to have very different behaviors in the rule transitions. You might wonder like how many actually different loops there are, which to me feels like there aren't all the many unique loops, because this is for n of 21. It's covered by the zoom, but there's a 1 hiding in there. N of 21 means that there are n at 2 to the 21 over 21 possible nodes, which it's a lot of nodes to like deal with. And there are only 20 different unique cycle lengths in here. And again, you can see that there's like a group that likes to set itself apart compared to the rest. And if we take a look at what the longest cycles are compared to the number of components, you can see that there's a bit of a trade-off, because as you might imagine, if you have very, very long cycles, then the number of components, cannot be like extreme, because otherwise like you've used a lot of your nodes in a single cycle that has to be part of the same component. And we can see this interesting structure where you see that there is like a bulk with not that many maximum cycles apart, and a few that stand out above the rest. Again, these rules that have been shown to be computationally chaotic, so have like quite diverse behaviors. And I would like to conclude on this big picture, which I personally find very nice. I feel like maybe someone should put it on a t-shirt or something. And it shows for all the 256 possible rules, number 0 in the top left and 256 in the bottom right, sample, basically the largest weakly connected component for n equal 11. Why 11 is just that there's a lot of nodes, and PDFs are not like very happy to have even more than this. And I consider this to be like a good trade-off between simplicity, visual interestingness, and rendering on a digital device. And I find that there's like a lot of interesting structure that I'm still investigating. Everyone that has seen this has asked me why there's a diagonal of loops. I have tried to have an answer before today, but I haven't found one yet. If anyone has some intuition, please feel free to share. There's also some other, maybe a bit more subtle behavior where here, like on this, oh, too far. Gonna let me go back. Okay, let's see. I have to like scroll like a peasant. On this column here, there's also some other hidden structure where it alternates like every other row kinda changes in its behavior. It becomes more apparent if you check how many nodes are part of the larger component. Might not be so visual, appealing right now. This is what I have. Thank you for listening. If there are any questions.